Okay, the second part of a three-part series on the video, and uh, hopefully you've gone through the first part and you saw how to calculate some of these equations up here. Now, in the second part of the video, um, I created this other section break, and in here I'm going to create the symbolic definition or the symbolic representation of the transfer function. And the transfer function, there's going to be two transfer functions we're going to look at. One transfer function is going to relate the output rotor angle as a function of the input armature voltage, the applied voltage to the armature windings. And then the other one, we have to reflect that angle. The actual homework problem asks for the output angle, so we have to reflect that rotor back through the 1:4 gear ratio system. One of the ways to do that is we create what are called symbolic variables in MATLAB, and the syntax for that is SYMS, S-Y-M-S. So I'm going to create a couple of them. SYMS G sub 0, that's going to be our output, and G sub M, that's going to be our motor transfer function. So we have an output transfer function and our motor transfer function. Now, all these are defined up here, and those are good. So we'll be able to use those parameter values in our symbolic definition. One of the things you still have to do in the hard work or heavy lifting is you still have to come up with the transfer function, and you have to look at that. If you're having troubles getting the transfer function, I have posted the solution symbolically in Blackboard. So go ahead and if you want to look at that and download that and take a look at that. But the motor transfer function at one step is equal to 1 divided by the quantity, s cubed. I'm going to put my s cubed in brackets. Times LA times JM divided by KT. Plus s squared times BM times LA divided by KT plus JM times RA divided by KT plus S times BM times RA divided by KT plus KB. And that should do it. Now, I can run this section. I'm going to go up there and just run the one section. We'll see what we get. Not a very good looking form of the function. There's a couple things we can do to clean this up. One of them is to use the command VPA, and VPA stands for variable precision. And so, for example, if I do VPA with 3 decimal places of precision, and we run that section, you'll see it comes and cleans it up a little bit. But we still have the problem with the leading coefficient probably isn't what I want to see. Not that we couldn't use this, but maybe we want to look a little bit differently at this function. So it's really easy because now that I know what this leading coefficient is, I can grab this whole leading coefficient, and if we want to factor that out, I can, I'm just going to cut that. And when I do that, remember, I have to now divide the numerator by that value. Let me put that in the numerator. So I used a paste command. Get rid of that one right there. And there's our numerator. But we also need to divide out these terms right there with that. I'll divide the first one. And let's see, I think I need to divide the second one as well. And there now I've just symbolically done the factoring, if you will. And let me run the section on that and see what we get. And that looks much, much better, but still not necessarily the answer that we're looking for, because I have to reflect it through the gears, and I'm going to do that. So our output is equal to, I'm going to use the VPA command on this, NM, put some brackets around that, our gear ratio, NM times NL, times GM, and again, I'm going to use three decimal places of accuracy. I'm going to save the file so I don't lose this, and now I'm going to run the section. And there is the final answer. And go ahead and take a look at that. Some of you have factored out the S in yours. And so that's how you use symbolic variations to solve problem 3. I'm going to go a little bit past this point in the next video. I'm going to do one last video, and in that video we're going to show how we can now use the transfer function to actually get the output step response for maybe we want to look at the velocity of the motor. And I'm going to do a couple things, because now we can go and actually make our inductor 0 and see what happens. So we'll come back to that video.